This is David Loeffler, and he's going to go on with the third talk on Hida theory and p-adic L functions. So on explaining explicit reciprocity laws and p-adic families.
Well, thank you. And I'll just recap briefly where we were at the end of Sarah's talk. So we have pi corresponding to a local system of weight R1, weight R1, R2. Sarah's just shouting at me that I need to write bigger.
Oh man, yeah.
And it's Klingon ordinary. And we have this p-adic L function, LP pi, such that LP and LP pi evaluated an integer j. There's two cases corresponding to my talk and Sarah's talk earlier. So this is a critical value of the complex L function for j a little bit, so j non-negative and sufficiently small. And I'm going to call that set sigma crit. And it's equal to Bloch-Kato log of an étale cohomology class for j equals -1 minus R2 plus Q. So obviously this range stops at -1, so these two ranges don't overlap. So this is what Sarah called the geometric range, sigma John. Sorry, should have made my bracket much larger. And what we want is information about Galois cohomology classes but in the critical range. So we want that information about the vanishing or non-vanishing of the complex L function at some critical value should have some direct consequences for some class in cohomology. And we want to do that by somehow dragging this information we have from the geometric range to the critical range. So now we assume pi is also Siegel ordinary. And that means that our cohomology classes interpolate when you change Q. So somehow Klingon ordinary was the right condition for the L values to vary analytically with the cyclotomic twist, but Siegel ordinary is the right condition for the cohomology classes to vary in a cyclotomic family. So I'll just write LSZ because it's the same citation as in Sarah's talk. So if I write ZQ for the class in cohomology over here, which is in H1 Q B pi star minus Q, interpolate. So more precisely, lambda is the usually Universal algebra. And I have a universal character from ZP star into lambda star. So then there's a class in some lambda module that interpolates all of these guys for varying Q. And so it makes sense, having got this thing, to ask what happens if you specialize it at a Q that's outside this geometric range. So we can specialize into the critical range. So the question makes sense. And you can conjecture that this should be related to a value of the L function. And that's what we're going to prove in the end. And just a reduction step along the way, Perrin will use big logarithm. It's sometimes called a regulator, but I hesitate to call it that because that name's used in a rather different sense in this theory. So if star is that group. And I wanted to write it's a map from star to something. In fact, it's a map from some subspace of star to something, but that subspace contains Z psych, so it's okay. So it lands in the dual of the H2 cohomology space associated to pi. So this we know from comparison isomorphisms is isomorphic to a graded piece of d de Rham of the Galois representation, which is how it comes up here. I'm going to define something that I call the Motivic p-adic L function, which is going to be the eta that we had before, so the coherent U prime eigenclass associated to pi. So that's a well-defined element of the OSR algebra. It's a well-defined measure on ZP star. At the moment, we don't know anything much about it. Could be 0, but at least it's a well-defined object. And our goal is to prove that LP mot pi is equal to the analytic p-adic L function LP pi. And this is what we call an explicit reciprocity law. So those of you in the audience who've worked with Euler systems and p-adic cohomology classes and so on in the past will already know this. But once you have a statement like this, lots of very powerful applications follow in a fairly well-established fashion. There's a standard machine you can run. So once we have this, the path is open to lots of powerful applications that I'll come back to later. This is really the main goal, the main difficulty in this theory. So we know these agree at the integers in sigma geom. Which we're thinking of as a subset of the formal spectrum of the OSR algebra. And it would be nice if we could just say, yeah, they agree at these points. So by analytic continuation, they agree everywhere. But unfortunately, this guy's a finite set. So there's no hope whatsoever of it being Zariski dense in this positive dimensional rigid analytic space. So just to remark, just a prerequisite for this goal making sense we made some auxiliary choices along the way in defining both LP and LP mot. And it turns out they're the same auxiliary choices. So in fact, a better way of thinking of these is as linear functionals on some space of test data, and then we're proving the equality of linear functions. So obviously we're going to choose the same data for both of them, but it's just comforting if they're going to be equal that this is a well-defined statement. So that's just the setup, and that's what we're trying to prove, this explicit reciprocity law. And here's the basic idea for doing it. So we have three parameters, three things controlling the situation. There's the two weights of pi, R1 and R2, and there's also this cyclotomic parameter Q. And if you keep these fixed and you just vary Q, you're stuck in this finite set sigma geom, and there's not a lot you can do. But we're going to get some mileage by varying other parameters. So there's three kinds of p-adic families for G. You can vary it in what we call Klingon type, where you fix R2. There's a Ziegel type families. And there's kind of full Borel type families. Where you make no condition. And somehow, if you want to put pi in a family, the Borel type families, you need to make a stronger finite slope assumption on pi, but on the other hand, you get more for your money. You vary it in more parameters. So these families have smaller dimension, but they might see more classical forms. But in any case, what we want to do is to use this freedom to make the set sigma geom big. So if you remember this set sigma geom, which was defined a page or two earlier, it's an interval, and the length of this interval is R2. So we want to be able to make R2 bigger. So the set of Q satisfying this inequality for a fixed R2 is not dense, but the set of pairs is dense in W times W. And I'm going to draw a diagram here, which I actually stole from a book by Daniel Del Borgo. If you imagine this variable is R2, this variable is Q. if you just look at R2 being fixed, and there's somehow only finitely many lattice points on this line. But if you look at all points satisfying these conditions, you've got some big region, and that's actually dense, rigid analytically in the whole plane. So as I said, I stole this from a book by Daniel Del Burgo, where he was using the same idea for Hida families for GL2. And it's quite a common trick in studying p-adic functions and Euler systems. Oops, sorry, what's here? I've run out of plain paper, it seems. That's better. So we want to say, can we vary all of the objects in our problem in these kinds of p-adic families? And one thing is fine. The Euler system classes vary analytically in all of the above kind of families. So we check this in the LSZ paper for Siegel type families. We didn't use the Klingon and the Borel type ones directly in this project, so we stopped at that. But my student, Rob Rockwood, has actually managed to generalize the approach and show that you get variation in all the kinds of families it makes sense to have here. So on the side of Ital cohomology classes and their Galois images, we have very good understanding of variation in families. But there are really two problems. So one is probably more or less solved now. It's not so clear. If we want to construct the analytic p-adic function in a big family, we need understanding of variation of these things here. And the non-overconvergent version of the theory, so this is higher Hida, not higher Coleman theory. This only exists in Klingon families. And this is really a problem for us, because in our construction, we work with the Eisenstein family, Katz's Eisenstein measure, as I called it, and that's really not overconvergent. So this came up a bit in my talk yesterday, why we use Hida and not Coleman theory and impose an ordinary rather than a finite slope condition. And this is why, because we need to be able to use this non-overconvergent family as an input along the way. So that's one problem. So I'm led to believe this is more or less solvable. It's just that George and Van Sons have concentrated on other things that seem more important in the meantime. But it certainly wasn't available in the literature at the time we were working. The other problem is more subtle, but in many ways more severe. And this is about how we construct LP Motivic. So to construct LP Motivic, we used a family of cohomology classes, we used a regulator map, and we used a comparison isomorphism. pi eigenspace, of course. So this is part of the Isomorphism isomorphism, which we heard a lot about in Fabrizio's talks earlier this week. And we need this in families. And we specifically need either a Siegel type or a Borel type family, because we want to make R2 large, as we said here. So a Klingon type family where R2 is fixed is really no good for these problems. In a Klingon type family, you can make sigma crit be really wide, but that's not the problem we're trying to solve. We're trying to make sigma geom wide. So Fabrizio explained an approach to getting isomorphisms a bit like this in a Klingon type family, but we need it for a Siegel type or Borel type family. And this is one of these things where you first looked at it and you think it's self-evident, because we're so used to thinking of comparison isomorphisms as being canonical identifications that the idea that you need to do something to study them is maybe requires a bit of mental adjustment. But it really is genuinely not obvious in this case. So what we're going to do is we're going to cheat. The original title of this in my notes, I've toned it down a little bit, was A Beautiful Theorem and an Ugly Trick. And it's a beautiful theorem of somebody else and an ugly trick of ours. And what we're going to do is we're going to make a comparison between objects on GSp4 and objects on GL4. I don't know a good notation for this. I can't draw capital Pi's, so I'm going to make it be pi hat. So the fact we have a degree 4 L function for GSp4, whenever you have an L function, you should also have a functorial lifting to GLN. So there should be a lifting to GL4. And this is known to exist. And better, if pi is cohomological, then so is pi hat. And you can use that to put them in families. So if any of the above types, so if pi underline is some family on G, we get some pi underline hat on GL4. And this can be a Siegel type or a Klingon type or a Borel type. So now here are two theorems. So the first theorem is due to Mladen with his co-authors, with Fabian Januszewski and with Anupam Raghuram. They proved that there is a p-adic L function for pi hat. So in effect, this shows that when we constructed p-adic L functions for pi, we were reconstructing a known object because it's interpolating the same thing. So in fact, it's the same p-adic L function up to scale.
So you're in the Klingon case here?
Let me say pi is ordinary here, Borel ordinary.
Okay.
So from now until the end of this talk, all my pi's are going to be ordinary for the Borel. That doesn't mean my families are all going to be Borel type families. It means I can put things in Borel type families if I want, but I won't always do so. But I always have pi ordinary. There's an extension of this theorem, which is in forthcoming work of 3 people who I believe are all in the audience. I'd better get this right. So there's a p-adic function for families of lifts. And these are the kind of families on GL4 that correspond to Klingon families on GSp4. And this can be extended to Borel type families, actually. So this is not written up, but the methods are there in a paper I wrote recently about spherical varieties and norm relations. And in fact, it works in general. Lifts from G spin 2G plus 1 to GL 2G NEG. So you get G plus 1 variable L functions in those kinds of families. But it's very much a refinement of the same idea as in these 2 constructions here. So these constructions are essentially Betty cohomology constructions. They're in some sense like modular symbols. Which is the GL2 case. So what we're going to do is we're somehow going to bounce off the fact that you have p-adic functions in Klingon families on one group and in Borel families on a different group. And there's a minor technical point. You need to compare the Whittaker period on G with a period on GL4 and it's actually a product of 2 periods. If you remember way back at the beginning of my talk yesterday, I wrote down a formula for L functions, and it actually was a formula for a product of 2 values of an L function. And we somehow kept one of those fixed and varied the other and absorbed it into the periods. And here it is coming back again, because the GL4 integral formula really doesn't see, it really just sees 1 L value at a time. So somehow you have to remember the second one you absorbed into the periods, and that's why we get the product. And that will bite us again in this talk.
With the product of the 2 L values, that's very much like in Cato's Euler system.
Yes, indeed.
Where he also sees the product of 2 L values and one gets absorbed into the period.
Yes, quite. Thanks, Sarah. That's a very good point. So this is closely parallel to something you see in Cato's theory, with the Rankin-Selberg L function of an Eisenstein series being the product of 2 copies of a standard L function for GL2. So the upshot of this is that if pi underline is a Siegel type family, and it's over some aphanoid U in weight space around R2. So specialization at R2 is the pi I had to start with. We have an LP pi hat underline. And if you want to make explicit the dependence of the periods, I think valued in, I just mean it's an element of. And this is some module that's basically a Betty cohomology eigenspace associated to the family lifted from pi, and it's free of rank 1 over OU. So normally one just chooses a basis and then defines a p-adic L function with some period depending on that choice. But we've written this in a more canonical way because we're going to need that a bit later. So going back to our world of Euler systems and Galois cohomology classes and so on, we have an LP mot of pi underline, which is an element of something very, very similar looking. So I should mention OW is the algebra lambda I had before, or some completion of it. And so this is restating the things I had earlier in the talk. So this is a graded piece of the de Rham cohomology attached to my Galois representation in a family. So again, it's free of rank 1. And what we'd really like would be a canonical isomorphism between this guy and this guy that would send this guy onto this guy. And it turns out that you know enough about this situation that you can just pluck such an isomorphism out of thin air. This is a really, frankly, rather strange argument. It seems to produce something like an Ishida-Shimura isomorphism literally out of nowhere. And the price you have to pay is you have to extend scalars to the fraction field of your little disk in weight space. So this is like an isomorphism of meromorphic modules over O of U. Which sends this guy onto this guy. And how are we going to prove this? So a nice thing which Mladen and his co-authors prove in their papers is that if this is, which is basically the length of the critical interval, is big enough, then this p-adic L function is not a zero divisor, because you have enough critical values that are not central values, so they must be non-zero by the convergence of the Euler product. So that's one thing you can do. So fix an isomorphism arbitrarily completely random isomorphism over OU, which you can do because they're both free of rank 1. So you can divide one of these guys by the other guy. On the other hand, you know if you evaluate this at R2 and J, and this guy's independent of J. That comes from all the regulator formulae in Sarah's talk, which show that for a given R2, there is an isomorphism between the fiber of this guy and the fiber of this guy, which actually sends this onto this. We don't know these interpolate, but at least it tells us that this ratio is independent of J. I should say for J in sigma geom. But on the other hand, if you just use the fact that the J and R2 such that J is in sigma geom are Zariski dense, you can conclude that this function LP mot over LP is in frac O of U, so it's independent of J. It doesn't depend on the cyclotomic twist, only on the weight. And now we go back to where we were before. This isomorphism between MB and M was arbitrary. So I can rescale it, and I'm going to rescale it to make this be 1. So I should mention that not only is this in the fraction field, it's a unit in the fraction field. So it's not identically 0, not identically infinity either, because we knew that this wasn't a zero divisor. And so this little information that comes from the regulator formula is enough that we can pull this isomorphism out of nothing, in effect. So just a remark. If we had somehow a native construction of the analytic p-adic L function on the group G, without using the Langland's functoriality transfer to GL4, And then we'd be able to run exactly the same argument, but with coherent cohomology in place of the Betti cohomology, and we'd get essentially for free a meromorphic interpolation of the Isomorphism isomorphism. So when we started on this project, we were thinking that we were really going to need to locate strong, powerful results about Isomorphism in families in order to study Euler systems and p-adic L functions. And somehow it seems to have worked out the other way around, that if you understand p-adic L functions and Euler systems well enough, the Isomorphism isomorphisms just sort of drop out of the sky. And this is actually quite reminiscent, again, as Sarah will point out, if I don't, so I may as well say it, that something like this also came up for GL2. In our work with Guido Kings, we actually were able to slightly strengthen the known results on Isomorphism isomorphisms in Hida families by using information about Euler systems. So there's one last thing to deal with before we can start mopping up the arithmetic consequences of this. And that's the fact that this is a meromorphic map, an isomorphism of modules over the fraction ring of O of U. So we need to do something to deal with the points where it degenerates. And we found a trick for this that we call the leading term argument. And this is to handle what happens when you specialize back to weight R2. I should have given this isomorphism a name. It had a name in my notes, but I forgot to write it down. So I'm underlining things in families, so I'm going to call it period underline in families. So and that's the name I'm giving to this isomorphism. So let T be a uniformizer at R2 in OU. So a function on weight space which vanishes at the point, which has a simple zero at R2. So what comes out of our constructions is that L of P mot underlying pi is going to be equal to T to the n for some n LP underline pi I guess this should be pi hat strictly. So this is why it was important to work in a Siegel type family, because for a Siegel type family, the local rings of the parameter space are the DVRs. So things blow up, they blow up in a very precise way. So the only possibility is that you have some power of the uniformizer. And if n is 0, we've won. And the problem is to deal with what happens if n is not 0. And n has to be positive. And if you look at this thing mod t, you just get the p-adic L function of pi itself. And thanks to these non-vanishing results that Mladen and his friends proved for us, this is non-zero mod t. And on the other hand, the left-hand side is clearly regular at t equals 0. So n can't be negative. So what if n is positive? And the sneaky thing to remember here is that the class Z cyclotomic is just the first layer of our Euler system. So this is just seeing the classes over the p cyclotomic tower. And if you choose an auxiliary integer m, you also have classes over the tame cyclotomic extensions as well. And you can kind of repeat this game for the classes at the mth layer. With what we call an equivariant p-adic L function. So this is some slightly fancier p-adic L function where rather than scalar valued, it takes values in some group ring and it interpolates the values of your L function together with its twists by these tame characters. But the point is the periods are the same. And the value of n, this vanishing order of the p-adic Motivic L function at t is going to be the same for all of these objects. So if n is positive, the entire Euler system for the weight R2 specialization, which is my original pi, is going to land in the kernel of the parameter U big logarithm map. And that means it satisfies a local condition for the Euler system, which is just far stronger than any Euler system deserves to satisfy. What we expect somehow is that its value under the regulator map should be some L functions. But if the value is always 0, we've got an Euler system that lands in a very small subspace of the cohomology locally at P. And there's a theory of core ranks for Euler systems due to Mazur and Rubin that you can use to show that it's 0. And hence the entire Euler system for the family is divisible by T. And so you can factor out the power of T, rinse and repeat. And you keep going until you get an Euler system whose image under the regulator map is a non-zero multiple of the analytic p-adic function. And that, well, it's not quite the goal that we had at the beginning, because maybe it's not quite the same Euler system we had at the beginning, but it's an Euler system, and its image under the big logarithm map is the analytic p-adic function. And that is strong enough for the application that we want to make. Sorry, is there a question? I heard a funny noise. Never mind. So let me just clean up some applications of this. What are we up to? Section 5. So I'm now going to assume an additional condition, which is that the image of Galois action v pi is large. So this is known to be true. If you fix a pi that's of sufficiently general type, and then you let p vary, then this is true for almost all primes p, thanks to work of I believe Loeffler and Zenteno.
David.
In any case, these large image results are well understood.
David, automorphisms of v pi.
Oh, sorry. Yes. Yeah. So there's a map from into GL of v pi that actually lands in GSp of v pi, and we want that image to contain GSp of a lattice.
You want the Lie algebra image to be large? Or the residual one?
For this, I probably need the residual image to be large for the statements I'm giving here. I mean, it should work for as long as the image is open, so large in the Lie algebra, but we haven't checked the full details. So let's take it to be large, to be as large as possible. And the theorem is that if you take a j in the critical range, if L of pi j is not 0, then the Selma group over Q of v pi star minus Q is 0. So this is the Blockato Selma group. And this is what we call the Blockato conjecture in analytic rank 0 for the critical values of the L function. And I just want to note If j is not the central value, and often this interval of critical values is quite wide, so not lots of non-central values, then it's automatic that this L value never vanishes. So the hypotheses of our theorem are going to be satisfied. So the analytic rank is very often 0. And it's expected to be often true for the central values as well. I'm not going to go too much into that, but I just want to reinforce that these analytic rank 0 cases are already a very large part of the battle in proving the Bloch-Kato conjecture. And there's a second theorem, which is that the cyclotomic Selma group has a characteristic ideal I've been a little sloppy about how I define the periods. So my p-adic L function is only defined up to an element of qp bar star. So I can't hope for an integral statement here, although probably one could be formulated and maybe proved by these methods. But it's certainly true that it divides this in lambda tensor qp or qp bar. But the scalars don't matter so much. So this is one inclusion in the Iwasawa main conjecture.
Well, NC-Selma group is torsion.
Yeah, well, this is non-zero, so this implies this is torsion. So this is one inclusion in the Iwasawa main conjecture, and if pi is lifted from GL2 over an over a real quadratic field, we can improve this. So by comparing our results with those of Shin 1, then the full cyclotomic main conjecture holds for elliptic curves over, sorry, I'm losing my thread, over real quadratic fields. So one had proved the opposite divisibility. He had proved that the Selma group wasn't too small, and our result shows that the Selma group isn't too large either. And in this favorable case, we can actually control the periods integrally using a more refined form of this leading term argument, where as well as shaving off extra powers of t, you also shave off extra powers of p as well. And using an argument like that, you can get an optimal integral form of the main conjecture that actually shows that the upper bound coincides with the lower bound that one had already proved. So that gives a pretty powerful application of these ideas. And I think my time is up here. So I'm going to stop at that point, and thank you for listening.
Okay, so let's thank the speaker. Are there questions? I have a comment, David, and that is in Fabrizio's talk, actually, he had a Eichler-Shimura map in the Siegel case, but the image of the Eichler-Shimura going from H3 et al., it goes to modular form, so to an H0.
Yes, so I was talking about an isomorphism for the first graded piece.
I mean, if what Fabrizio said was true, I am not sure that there isn't a contradiction between these results.
Why should there be a contradiction?
Well, I mean, is the map that you have Heck equivariant?
Yes.
So then I think, but anyway, it's not my, I mean, we are not going to solve this question here. I just wanted to point out that that there is an Eichler-Shimura overconvergent Eichler-Shimura isomorphism. It's not an isomorphism, it's surjective, going to overconvergent modular forms.
Indeed, I had maybe focused only on the version of the isomorphism that sees the middle graded pieces, the GRA1 and the GRA2. But as you say, there's this story for the top graded piece, for the GRA3, which seems to be much more well understood. And Fabrizio, and in his joint work with you, seems to have understood this very beautifully. And our approach is somehow much more unsatisfying in that it really it kind of drops out from something that ought to have nothing to do with comparison isomorphisms. And there should clearly be a more natural direct construction. But yeah, I think these things are not in contradiction in any way.
Okay, let's hope not then. Are there other questions?
I have a question. So first of all, thank you for this wonderful series of lectures. I enjoyed them a lot. Thank you very much. So David, just a question, maybe it's stupid, just to understand a little bit better those periods. So somehow like this transfer from GSp4 to GL4 works well in families, right?
Yes.
And so this MB is a tensor product of two eigenspaces of the Betti homology for GL4?
Yes, the plus and the minus subspaces for complex conjugation.
Ah, I see, okay.
So the toy version of this in some sense is that for an elliptic modular form, the Peterson norm, which is sort of analogous to our Whittaker period, is up to like some explicit power of pi. It's a rational multiple of the product omega plus times omega minus.
Yep.
And that's in some sense maybe what we're doing here, and something a bit like that when we're comparing these periods via them coming up from an L value.
But David, I mean, you pointed these difficult relations of periods, which are, well, sometimes solved rationally, but certainly not integrally. But at the end of the day, you end up comparing p-adic periods, right, with your argument, analytic argument. So you don't really care so much about the Archimedean periods.
Right, but you have several different, I mean, you start with an L value that is a generally transcendental complex number, and you have various different ways of producing a complex number that you can divide it by to get something algebraic. And our method will allow you to compare different choices of that for up to p-adic units. So this is the period that compares the Archimedean to the.
You're using the family argument to somehow show what you want without genuinely proving period relations.
In some sense, yes. So what we can prove from this, for instance, if I go to the theorem I had at the very end.
As a corollary, maybe you'll explain now, but you're certainly not as an input anyway, and now you'll explain why maybe you get a corollary on these period relations, but you don't have an input from these relations.
Indeed, I mean, this method gives period relations as a corollary. It gives the integrality of some ratio of periods. So, for instance, if you apply this to one of these elliptic curves lifted from one of these lifts from an elliptic curve for a real quadratic field, you would get some kind of integral comparison between the period for the GL2 over F and the periods for its lift to GL4 over Q.
Mm-hmm.
The comparison isn't quite perfect. I mean, if you assume some sort of mod P non-vanishing result for equivariant L functions, that you can always find some M such that the Z mod M equivariant p-adic L function is non-zero mod P, then you get an exact on-the-nail comparison of the periods involved.
Yeah, it's very nice, and it goes back to Stevens, this idea to use weight variable, and yeah.
To Maser Kitagawa also.
Maser Kitagawa, yeah.
I have another question.
Please.
So like, to which extent one could use these sort of ideas for GSp4 to attack, let's say, cap forms? So let's say some Saito Kurokawa lifts from a Bianchi modular form rather than,
well,
because I recognize that you use, like, for instance, I mean, there is this condition on the image of the Galois representation that it's certainly false for Saito Kurokawa lifts, but
indeed, but depending on what kind of image you have, you can often do something. So, so the real quadratic case here, and the image isn't open in GSp4, but it's open in some smaller subgroup, and that turns out to be enough. And the Bianchi case, one would expect something like that to work, but there is a problem, which is that the Bianchi guys don't vary in sufficiently big families. You don't. You have some theory of p-adic families for Bianchi forms, but the families are not full dimensional over weight space. And somehow it's very, very unclear. Maybe Daniel or Chris Williams can correct me on this, but I think it's very poorly understood what the support of such a family over weight space should look like. So we're hoping to attack that sort of problem in future, but it would require a better kind of native construction of p-adic L functions in families on G, without this trickery of lifting to other groups.
I just want to make a remark there. I mean, the large image assumption comes from the Euler system machine, so for which one needs the existence of certain elements, I mean, in the image of the absolute Galois group of Q. And I mean, the question there is whether that is satisfied, and it is certainly not necessary, I mean, that the image be open.
If I could add one more thing here as well, there are lots of different kind of non-general type Siegel modular forms. So these lifts from imaginary quadratic fields, twisted Yoshida lifts, these are reasonably easy to work with in some sense. The split Yoshida lifts that are coming from GL2 times GL2 are a little more difficult because the L packet is not stable, so you get some eigenspaces missing in effect. You contribute to either H0 or H1, but not both. And the construction of the p-adic L function, I think, still works, but the construction of the Euler system is more difficult because you land in the wrong Galois representation. And as for cap forms, I have no idea, because for cap forms, it's like the certain it's difficult to somehow separate the boundary part of the cohomology and the cuspidal part, because somehow those Hecker eigenspaces overlap. So some of the special cases are easier than others. So, for instance, symmetric cubes of elliptic modular forms give you pies where the image is fairly small, but it's still large enough to prove something. And we have a short paper handling that case. But yeah, the Saito Kurokawa case does seem to be hard.
You have a paper on a sim cube of an elliptic curve?
Sim cubed of a modular form in general, yes.
Well, the elliptic curves case is actually handled by Heining Wang via a different method.
Good, fair point, yes. So in general, there's another approach to the symmetric cube that gets you at the central value, by using arithmetic level raising congruences methods on the triple product. But this method can get at non-central values of triple product L functions as well. So there is certainly some Galois representations that you can get at from several different Humora varieties.
Okay.
I would like to make just one remark. Sorry, Adrian.
Go ahead. Go ahead.
So what we are currently looking at is the deformation to parallel weight 2. I mean, to get at abelian, modular abelian surfaces. So, I mean, this is work in progress. And I mean, we hope, I mean, that now with the tools, I mean, that Boxer and Pilloni have introduced, I mean, that we are able to deform, I mean, to parallel weight 2 and then get a BSD, well, the rank part of DSD in analytic rank 0.
So that's the long-term project.
Okay. Any more comments, questions, anything? If not, I would like...
should thank the organizers, no?
Exactly. Let me
say that as well. It's as the last speaker, perhaps this falls to me, but I'm sure that all of us here would be very, very happy to thank the organizers for this wonderful workshop. And it's obviously not quite the same as having a workshop in real life, but as far as an online workshop goes, this has been about as good as I can possibly imagine it being. So it's been a fantastic job. Thank you.